Welcome dear students. Today we will study about a rectangular potential well. In this article we will use quantum mechanics. We will solve Schrödinger wave equation and prove that in a well a particle cannot have any arbitrary value of energy. Rather, it will be having a well-defined energies. So for this, consider a potential well given by Vx. Vx is a potential of the well whose value is 0 for x less than 0, minus V naught for x greater than 0 less than a, and again 0 for x greater than a. And in this well we consider a particle in a well we have a particle in a well which is bound to it. So as particle is bound to the well, so its energy will be less than 0, and we will put that energy is equal to minus W, and W is the winding energy of the particle. And diagrammatically we will represent the well like this. Say this is x-axis, this point is x is equal to 0, this point is x is equal to a, and this is the y-axis, and along the y-axis we take the value of potential, and our well is like this: 0, this is a region x less than 0, potential is 0, and between this the value of potential step is negative. It is along a negative y-axis, value is V naught. This value is minus V naught because it is along minus y-axis, and here again this region is x greater than a, potential is 0. So we mark this as region 1. This is the region 2, and this is the region 3. And this is the particle that we are dealing with. It is in the potential well, bound to the well. So now firstly we will deal with this problem classically. So what classical mechanics tells us about this situation? As energy of particle is less than 0, so particle has to stay within the well. The particle has to stay within the well because it is bound to it. It cannot leave the well. When it moves towards the side of well, it will strike with them and bounce back. When it moves towards the sides of well, it will strike with the walls, of well and bounce back. And will never leave the well. It will always remain within the well. Keep on moving like this. Striking the balls, comes back. Again moving like this, striking the balls, again comes back. But it will always remain within the well. It will never going to leave the well. So this is the classical view. But quantum mechanically, we have different findings. So for that, we will solve Schrödinger wave equation. Quantum mechanical view. So according to Schrödinger wave equation, d2 psi by dx2 2m upon h cut square e minus v psi is equal to 0. So this is our Schrödinger wave equation, and we will solve this equation in different regions. So in the region 1, v is equal to 0. So our equation will reduce to d2 psi by dx2 plus 2m upon h cut square e minus 0 psi, and the solution of the wave function we represented using psi 1. So it will be d2 psi 1 upon dx2 plus 2me upon h cut square psi 1, it is equal to 0. So as we have substituted E is equal to minus W, so this wave equation will reduce to 2mw upon h cut square psi 1, it is equal to 0. So dear students, for the general solution of this, we write here iota square and we put 2mw upon h cut square, it is equal to k1, and we mark this as equation number 1. So our equation will reduce to iota square k1 square psi 1 is equal to 0, and the solution for this is given by psi 1. It comes out to be a e raised to power k1x plus b e raised to power minus k1x. So this is the solution. But when we look at the well, what we found that in the region x less than 0, and our wave function should be finite at x is equal to minus infinity in this region. So if we substitute x tending to minus infinity, then this term for x tending to minus infinity, this term will be infinite. So wave function will be infinite. So that is not allowed. So to avoid this, we put b is equal to 0. So in the region 1, solution for the wave function will be e raised to power iota e raised to power k1x. So this is the solution of the wave function, and this is the allowed solution. The term which is introducing infinite term has been made 0 by putting its coefficient equal to 0. So now we have solved the Schrodinger wave equation in region 1. Now we switch to region 2. So in the region 2, v is equal to minus v naught. So our Schrodinger wave equation, it will reduce to E is equal to minus W minus v naught psi 2. Psi 2 is the solution in the region 2 of the Schrodinger wave equation. So we will be getting this. So for the solution of this, if we put square root of 2m upon h cut square v naught minus w, let it be k2, and we mark this as equation number 3. So our wave equation will be simplified to this, and its solution is given by psi 2, it is equal to c e raised to power iota k2x plus d e raised to power minus iota k2x, and we mark this as equation number 4. Now moving to region number 3. Again potential is 0 in region 3. So Schrodinger wave equation, it will be having solution psi 3 So we can also substitute the value of E equal to minus W, so that will be minus sign here because E is equal to minus W. So we can write it like this: plus iota square. So this is a little mathematics. Iota square is equal to minus 1. So put, we have already used this substitution. What we have supposed this is equal to, k1. So substitute it. Iota square k1 psi 3, it is equal to 0, and the solution for this equation is given by psi 3, it is equal to f e raised to power k1x plus g e raised to power minus k1x. but it should be a allowed solution. But when we check for x tending to infinity in region 3, because in region 3 is x greater than 0, so x greater than a, sorry, it is x greater than a, so x tending to infinity lies in this region, x tending to infinity lying in this region. So when we check the validity of the solution for x is equal to tending to infinity, then this term, it will be e raised to power infinity, it will be infinity. But our solution should be a allowed solution at x is equal to infinity as well. So to do this, we put f is equal to 0. So solution in the third region will reduce to only one term, k1x. So we mark this as equation number 5. So we have 5 equations. We have solved the Schrodinger wave equation in different regions. So now we will apply the various boundary conditions. So applying boundary conditions one by one. So the first boundary condition is psi must be finite and continuous at x is equal to 0. So psi 1 at x is equal to 0 should be equal to psi 2 at x is equal to 0. Because x is equal to 0 is the boundary between the region 1 and 2. So this is the boundary between the region 1 and 2. That's why psi 1 is equal to psi 2 at x is equal to 0. So when we select the solutions for psi 1, when we put the value x is equal to 0, this term will be a, and for psi 2 it will be c plus t. So this will reduce to a is equal to c plus t. So this is our equation number 6. So similar boundary condition, psi must be continuous and finite at x is equal to a as well. Psi must be finite and continuous at x is equal to a as well. So x is equal to a is a boundary between region 2 and region 3. So if we substitute the values for psi 2 solution, equation number 4, it will be c e raised to power iota k2a, c e raised to power iota k2a plus d e raised to power minus iota k2a. It is equal to g psi 3. Psi 3 is g e raised to power minus k1a. So we mark this as equation number 7. So applying the third boundary condition, derivative of the wave function, it should also be finite and continuous, must be finite and continuous at x is equal to 0. So d psi 1 upon dx at x is equal to 0, d psi 2 upon dx at x is equal to 0, they should also be the same. So now we will take the derivatives of the wave functions. So psi 1 is a e raised to power k1x at x is equal to 0. Second wave function is c e raised to power iota k2x d e raised to power minus iota k2x. We will first take its derivative and then we substitute the limit x is equal to 0. So firstly take the derivative a e raised to power k1x into k1 derivative of the power. Here c e raised to power iota k2x iota k2 derivative of the power d e raised to power minus iota k2x minus k2 at x is equal to 0. So when we put x is equal to 0, so it will be e raised to power 0 which is 1. So it is k1a c iota k2 minus d iota k2. So here k1a it is equal to iota k2 c minus d. So c minus d will come out to be k1a divided by iota k2. So if we multiply by iota divide by iota, so c minus d it will be iota k1a divided by k2. In the denominator iota square is minus 1. So we will mark this as equation number 8. So now we apply the last boundary condition. In the last boundary condition we have d psi by dx must be finite and continuous at x is equal to a. So d psi 2 upon dx derivative of the wave function in region 2 at x is equal to a, derivative of the wave function in region 3 at x is equal to a, because x is equal to a boundary divides region 2 and 3 respectively. So when we write the wave functions, first it is c e raised to power iota k2x plus d e raised to power minus iota k2x at x is equal to a, g e raised to power minus k1 at k1x at x is equal to a. So psi 3 is, yes, equation number 5, g e raised to power minus k1x. Now we take its derivative. So when we take the derivative, it is c e raised to power iota k2x into iota k2 d e raised to power minus iota k2x into minus iota k2 at x is equal to a, g e raised to power minus k1x minus k1 at x is equal to a. So when we substitute the values, firstly we take iota k2 common. So it is c e raised to power iota k2a minus d e raised to power minus iota k2a minus k1 g e raised to power minus k1a. So when we solve this, we will be getting c e raised to power iota k2a d e raised to power minus iota k2a minus k1 upon iota k2 g e raised to power minus k1a. And this minus, it can be replaced by iota square. One iota cancels, so it will be c e raised to power iota k2a d e raised to power minus iota k2a. It is equal to iota k1 upon k2 e raised g e raised to power minus k1a, and we mark this as equation number 9. So now we have 4 equations, 6, 7, 8 and 9, and now we will solve these equations to find our constants that we have used in the solutions. So now we add equation number 6 and 8. So when you add equation number 6 and 8, it is c plus t, c minus t. So when you add, it will be I think I should firstly write the equations by this side. C plus d is equal to a, this is equation number 6. C minus d, it is equal to iota a k1 upon k2 with negative here, this is equation number 8. So when we add these two, it will be 2c, a common, 1 minus iota k1 upon k2. So c comes out to be a by 2, 1 minus iota k1 upon k2. So subtract 6 and 8. So it will be 2d is equal to a. When we subtract, this minus sign will change to positive sign. A is common, so it is a by 2, 1 plus iota k1 upon k2, and this is equation number 11. So now two equations are left, 7 and 9. So firstly we add 7 and 9, then we subtract 7 and 9, add 7 and 9. So I think firstly I should write down 7 equation and number 9 equation here. So it is c e raised to power iota k2a plus d e raised to power minus iota k2a, it is equal to g e raised to power minus k1a. And number 9 equation is, this is number 7. 9 equation is c e raised to power iota k2a minus d e raised to power minus k2a, it is equal to iota k1 upon k2 g e raised to power minus k1a. This is equation number 9, and when we add these two, we will be getting 2c e raised to power iota k2a, it is equal to one plus iota k1 upon k2 g e raised to power minus k1a. So value of g, firstly we substitute the value of c here from equation number 10. A by 2, 1 minus 2, a by 2, 1 minus iota k1 upon k2 e raised to power iota k2a, 1 plus iota k1 upon k2 g e raised to power minus k1a. So 2 cancels here, a k2 minus iota k1 upon k2 e raised to power iota k2a, k2 plus iota k1 upon k2 g e raised to power minus k1a. K2 cancels, so capital G comes out to be k2 minus iota k1, k2 plus iota k1 a. This term, it will become plus k1a e raised to power iota k2a, and we mark this as equation number 12. Now we subtract equation number 9 from 7. Subtract equation number 9 from equation number 7. So we will be getting 2d e raised to power minus iota k2a. Here when we subtract these two, here we will be getting plus, here we will be getting minus. These two terms will cancel out, they will add up. So it is 1 plus here. Okay, when we subtract this, negative sign will be here. 1 minus iota k1 upon k2 g e raised to power minus k1a. So substituting the value of d, it is a by 2, 1 plus iota k1 upon k2 e raised to power minus k2a, 1 minus iota k1 upon k2 g e raised to power k1a. So 2 cancels here, and when we take the LCM, it will be k2 plus iota k1 upon k2 e raised to power minus k2a, k2 minus iota k1 upon k2 g e raised to power minus k1a. K2 cancels, so g comes out to be k2 plus 1 plus iota k1, k2 1 minus iota k1 a e raised to power plus k1a e raised to power minus k2a. So we mark this as equation number 13. So equation number 12 and 13 both are values of capital G. Equate them. So from 12 and 13, what we will be getting? k2 minus iota k1 upon k2 plus iota k1 a e raised to power k1a e raised to power iota k2a, k2 plus iota k1, k2 minus iota k1 a e raised to power k1a e raised to power minus iota k2a. So these two terms, they will cancel out. So what we are left with? We are left with cross multiply these two, k2 minus iota k1 square e raised to power iota k2a, k2 plus iota k1 square e raised to power minus k2a. So when we square these two, k2 square plus iota k1 square minus 2 iota k1 k2 e raised to power iota k2a, k2 square iota k1 square 2 iota k1 k2 e raised to power minus iota k2a. So it is k2 square k1 square 2 iota k1 k2 e raised to power iota k2a, k2 square minus k1 square 2 iota k1 k2 e raised to power minus k2a. So when we try to solve this, it will be this term, it can be written as k2 square minus k1 square e raised to power iota k2a minus e raised to power minus k2a. this term, it will go on this side carrying this coefficient, becomes negative 2 iota k1 k2, and this term it will go on other side, becomes positive e to the power k2a plus e raised to power minus k2a, and these can be written as the trigonometric functions 2 iota sine k2a, 2 iota k1 k2, it is equal to 2 cos k2a. 2 iota cancels, so it will be cos k2a sin k2a, it is k2 square minus k1 square upon 2 k1 k2. So this is cot k2a, it is k2 square minus k1 square divided by 2 k1 k2, and we mark this as equation number 14. So we take 2 on the other side, 1 k2 cancels, so it is 2 cot k2. The value of k2 is 2m upon h cut square, v naught minus, we take a square because this is under the root. It is 2m upon h cut square, v naught minus w square root, divide by 2m w upon h cut square. So simplifying it a little bit, p naught take common, so put equal to alpha equal to beta. So the above equation will reduce to 2 cot alpha beta it is equal to this term, it will be alpha upon a beta, alpha upon a beta. And what about this term? This term we will solve. We will solve it here. 2mw upon h cut square. So we simplify it, v naught minus v naught, we add and subtract the term v naught. So we will separate the terms, 2m v naught upon h cut square plus 2m upon h cut square w minus v naught. So it is 2m v naught upon h cut square minus sign 2m upon h cut square v naught minus w. We again take here common v naught 1 minus w upon v naught. And what is this? It is alpha square by a square minus, this is alpha square by a square beta square. So when we take this, it is alpha by a common 1 minus beta square. So we substitute this value here, alpha by a 1 minus beta square, alpha by a 1 minus beta square. This cancels out. So we are left with 2 cot alpha beta, it is beta by 1 minus beta square, 1 minus beta square by beta. And when we try to solve this, take the LCM, beta 1 minus beta square, it is beta square minus 1 minus beta square. So it is beta square plus minus 1 minus 1 plus beta square divided by beta 1 minus beta square. So it is 2 cot alpha beta 2 beta square minus 1 upon beta 1 minus beta square. So we mark this as equation number 15. So if we put beta is equal to cos gamma by 2, then the above equation will be 2 cot alpha beta, it is 2 cos square gamma by 2 minus 1 cos gamma by 2 1 minus cos square gamma by 2. So it will be 2 cos square minus 1, it is cos 2 theta cos gamma, it is cos gamma by 2 sin gamma by 2. If we multiply by 2 divide by 2, this 2 cancels here, this is 2 sin theta cos theta. So cot alpha beta, it is cos gamma divided by sin gamma, cot alpha beta, it is equal to cot gamma. And the solution for this is alpha beta, it is equal to n pi plus gamma, and we mark this as equation number, this as 16, this as 17. So this is the solution that we will be using right now. So from 15, as we substituted beta, it is equal to cos gamma by 2. So gamma by 2 is cos inverse beta. So gamma is equal to 2 cos inverse beta. Equation number 18. So from 17 and 18, so alpha beta, it is equal to n pi plus 2 cos inverse beta. So this is the solution of the Schrodinger wave equation for potential well. So now we are to solve this equation, 19 number equation. So it is very tough to deal with this equation mathematically. So we will solve this equation graphically. So this equation can be easily solved graphically. This equation can be easily solved graphically. and graphically we put y is equal to alpha beta and z is equal to n pi plus 2 cos inverse beta, and for n is equal to 0, simplified solution z we get 2 cos inverse beta. And when we draw the plot, along the x-axis we take beta, along the y-axis we can draw y for this function or z for this function collectively. So this is a straight line graph. Y is equal to alpha beta, and this plot, it is somewhat like this. Z is equal to 2 cos inverse beta, and both the plots they intersect at this point, and extending this on beta axis we will get this value of beta graphically at the point of intersection, and that will be our solution. This is allowed value of beta, allowed value of beta for the solution. And earlier we supposed beta is equal to 1 minus W upon V naught. It is equal to beta, and this allowed value of beta can be substituted here to get binding energy like this. Squaring both sides, it will be 1 minus beta square. So W, it will be 1 minus beta square into V naught. So as we have only one allowed value of beta according to point of intersection of the plots, then we will be having one allowed value of the binding energy or the energy of the particle in the potential well. So what is the conclusion? That particle in a potential well cannot have any arbitrary value, rather it will be having a well-defined value of energy. So this completes our today's lecture. Keep in touch for next lectures. Thanks a lot.